Okay, so good morning, everyone. So today we'll be finishing chapter 2 and making a start on chapter 3. And the last thing we want to do for chapter 2 is see an implementation of the Euclidean algorithm. So just to remind you, the Euclidean algorithm is the algorithm which tells us what the greatest common divisor of a pair of integers are. So you give it a pair of integers a and b, just as long as they're not both equal to 0, and you perform a sequence of integer divisions with remainder. And each time we start off by dividing a by b, we get a certain quotient and a certain remainder. Remember, the remainder is between 0 and b. The next division takes b, the second number of your pair, it becomes the first number of your pair, and the remainder becomes the second number of your pair, the previous remainder. This integer division, b divided by r1, produces another integer, another remainder r2, and the process continues. The next input pair is the second of the input pair, the second division, that becomes the first, and then the previous remainder becomes the second. You keep doing these integer divisions with remainder until you reach a remainder of 0. You've cleaned divisibility at the bottom. And the point is that all these integer divisions, they all preserve the greatest common divisor. So the greatest common divisor of the pairs that you're considering in each line is always the same. Okay? That relies on the lemma, just a basic property of definition of the greatest common divisor that we proved a couple of lectures ago. And the greatest common divisor at the end is easy to read off because it's the greatest common divisor of this number Rn and 0. So that just has to be Rn. The second thing that the Euclidean algorithm gives you is this pair of integers m and n. These feature in what's called Beasley's identity. It tells you what the greatest common divisor is, or it expresses the greatest common divisor as a certain linear combination of the input pair. Okay? So we've lived with this for a while. We're quite familiar with it. So before we move on to the next chapter, we just want to see an actual implementation of it. Okay. So how to program it up. Now, just this morning, I created accounts for all of you on the computer system SageMath Cloud. So when you check your email, there'll be an invitation sent from me there to sign up to the system, and when you do sign up to it, and there'll be a project there called Number Theory and Cryptography, and this file will be in it. And so this file that we're going to produce now will be in it. And it's also like a quick crash of an introduction to some elements of the Python programming language for them as well. Okay, so what we want to do is write this function, and we're going to call it myGCD because there's already a function called GCD, which it does the job for you. But we'll do some comparison between ours and its built-in function in a moment. So this is how functions are defined in Python. You have this def function name myGCD. You put the list of inputs there in brackets, and then you have a pair of colons. Python relies on indentation and white space to indicate the various execution blocks. So the fact that this has been indented automatically when I press return there, and that's part of the Python programming environment. So this is the basic outline of what the definition of a function looks like. You can have some code here implementing the function, and then at the bottom somewhere will be a return statement. And whatever appears after the return statement, that's the value that gets returned by the function when we come to use it. Okay. Now, this is going to turn out to be deceptively kind of easy and quick to program, and because of the nature of the algorithm. Remember that when we're trying to find the greatest common divisor of A and B, we kind of don't tackle the problem directly. We do this integer division with remainder, and then we say that, well, this tells us that the greatest common divisor of A and B is the same as the greatest common divisor of B and R. just those points that I was running through in the recap on the algorithm. So if someone asks us what the greatest common divisor of A and B is, well, we just say, well, it's equal to the greatest common divisor of B and R1. So we avoid the question kind of. And then they ask you, well, what's the greatest common divisor of B and R1? And we tell them it's the greatest common divisor of R1 and R2. R2 is the second remainder that comes up. We keep on telling them this. So we keep on avoiding the question, if you like, until at the very end we reach some kind of statement which is what is the greatest common divisor of Rn and 0? And that we can answer easily straight away because by definition of divisibility, the greatest common divisor of anything non-zero with 0 is the other number itself. Okay. So in a way, that's what we do to program it. Okay. If it's a case that one of the inputs is 0, then we're going to set the greatest common divisor D to be equal to the other number. Now you're familiar with from MATLAB by doing if statements and then else if and so on. In Python, this is the particular syntax used. So we have if something, then else if, because it might be that B is the 0 one, in which case the greatest common divisor D that we wanted to return would be A. So that deals with this case at the bottom. Okay? If the inputs that we give to the function A and B, if one of them is 0, then D, which is going to be the number that we return as the greatest common divisor, we set the greatest common divisor D to be the other number. So if A is 0, greatest common divisor is B from this pair. If it happens that B is 0, then the greatest common divisor is defined to be A. And otherwise, what we say is we set the greatest common divisor. Well, we just do the same thing that is done in carrying out the algorithm. When someone asks us what the greatest common divisor of A and B is, we avoid the question and say, what's the greatest common divisor of B and R1? Okay. So now, what is this? When you perform this integer division, what's the value of this quotient? The value of this quotient we can define it's the floor of A over B. Now, what's the floor function? The floor function, and this I believe is also appears in MATLAB. The floor function, when you call it on an argument x, is the greatest integer, the largest integer, less than or equal to x. Okay. So x can be like some arbitrary quantity, numerical quantity. So x appears somewhere on the number line, and the floor of x is simply the largest integer that you have. These are integer points, 1, 2, 3, and so on. The floor of x is the last integer before the quantity x itself. Okay. If x happens to be an integer, then the floor of x is equal to x. But if x is not an integer, if it's a fraction, some kind of fractional number between two integers, then the floor is simply the last integer before x. Okay. And so that's what this quantity q1 here, that quotient is in the integer division. It's the floor of A over B. So we can set q equal to the floor of A over B, and then simply set D to be my GCD of B. And what's the remainder R1? The remainder R1 is simply A minus B times Q. Now this looks kind of strange, and then we return D as the answer. This looks kind of strange. This looks as if I'm kind of breaking a rule here, because I'm supplying the definition of a function called my GCD. But in supplying the definition of my GCD, I've used the function my GCD. So in a way, that kind of shouldn't be allowed. I'm trying to tell the computer how to carry out the function my GCD, and then along the way I tell it to use the function my GCD. Well, while this looks like a kind of circular reference that could go completely wrong and mess the computer up, it is actually allowed. So it's an example of what's called recursion. And recursion is where, in computer programming, where you use, as part of defining a function, you use the function itself. Okay? So if you think what happens when the computer tries to execute this on any given pair of inputs, well, if A and B, if neither of them are 0, it skips out these two if statements, sets Q to be the floor of A over B, and this is effectively carrying out the integer division with remainder. It then asks itself, okay, now execute the function myGCD on the second number B, and this quantity here is R1. Okay? And it goes back into it again. Again, probably neither of them are 0. It comes down here, and then, well, it's going to perform the integer division again. Taking the original B, the original R1, performing the integer division with them. This quantity here now will be R2. This quantity here will be the R1 from the previous time. And it keeps going through it. And because these positive remainders are getting smaller, they're always positive, they're bounded below by 0, eventually it's going to reach a case where one of these if statements gets triggered. And when that does, it finally gets to the return statement at the bottom, and it returns the GCD to the previous version of where it was called. Then this keeps this kind of returning process unravels completely, and it gives you the correct GCD. So this little block of code is an example of some Python code implementing the greatest common divisor. Okay, and we can test it out to see if it does what we kind of think it does. So if I call my GCD on, well, let's just give it a 0 pair just to make sure that bit's working. Yes, if you call it on 5 and 0, it returns 5. So one of those initial if statements was triggered there. And we can call it on my GCD 0 and 5, just check that bit's working. Okay. So then if we call it on, say, a pair, genuine pair there, so my GCD in 25 and 15 gives us out the answer 5. Okay. We could give it a pair of large inputs, just some A and B there, calculate the greatest common divisor of them, we get an answer 21, and we can check that using the already programmed version of the greatest common divisor, which is there already in the same system, and that agrees with 21 as well. Okay. You can also do this in MATLAB as well. I'll just show you briefly what the format. It more or less looks exactly the same. Just the syntax is slightly different, but you can also use this recursion technique when programming a MATLAB function. Just wait for this to appear here. I think it disappeared. It's called my GCD. Oh, I can show you the PDF version. Okay. I'll put this PDF version up on Moodle as well. This looks quite similar to what we were just doing, except the syntax is slightly different. So it's function, something equals my GCD of A and B. Now this one has actually been adapted to, as well as returning this quantity D, the GCD. You can see the format for getting that is the same. It's if A is 0, D is B. If B is 0, D is A. Otherwise, else D is set to the value my GCD of B and A minus the floor of A over B times B. So that's the integer division with remainder thing, and then calling GCD again on the smaller pair. What we can also see here is some information. The other commands are producing the M and the N that are needed for Bezo's identity. Okay, so we could have a think about how we might include that into the definition of our function to return those values. Now, okay, so now what we want is we want our function to return a triple of values, a D, an M, and an N. Okay. So the M is going to be the coefficient of A, and the N is going to be the coefficient of B in Bezo's identity, which gives us the greatest common divisor. Now, it's easy to, or there's no problem with deciding what M and N have to be in the 0 cases above. Okay. Because if the first one is if A is 0, and the greatest common divisor is B, and how do you write D as a linear combination, or how do you write B, since D, the greatest common divisor is B now, how do you write that as a linear combination of A and B? So how do you write B as a linear combination of A and B? Well, it's simple. You have 0 times A plus 1 times B. Okay. So the M and the N here is M is equal to 0, and the N is equal to 1. Okay, that's in the case where A is 0. In the case where B is 0, we get a similar thing. The greatest common divisor is A. And how do you write A as something times A plus something times B? Well, it's a 1 and a 0 again, except the other way around, because A is 1 times A and 0 times B. So the M is equal to 1 this time, and the N is equal to 0. Now, what's slightly trickier here is how we deal with the general case. Okay? Now, how we deal with the general case in calculating the GCD is we call the GCD function on the next pair. So the second element that we were at and the remainder that comes out of the integer division, which is this quantity A minus B times Q there. So if you think what happens when it gets returned, when one of these my GCD functions returns this triple, what gets returned, if you like, is D equals an alpha times B plus a beta times R1. Okay, because it will return back the greatest common divisor D, and it will return it back as a linear combination of B and R1. And we want to work out, well, if these coefficients come back to us, what are the correct coefficients to put in for A and B? In terms of the alpha and beta, and also in terms of this Q, which is the floor of A over B. Okay? Well, this Q here. And so what we do is we use this equation to rewrite R1 as a combination of A and B. So R1 gets replaced by A minus BQ. And then you can see what the coefficients are going to be. The coefficient of A is simply going to be beta, which is one of the coefficients that was returned to us last time. And the coefficient of B will be the one it was, alpha, and then there's a minus Q times beta here as well. Okay. So this rule tells you how to get the correct coefficients in the linear combination for A and B, which is the greatest common divisor, out of the coefficients that are there for the previous pair in the linear combination is equal to D and this quantity Q. See, these coefficients here now just rely on the alpha and beta that got returned before, and the Q. So we have to understand that the GCD now is returning a tuple of these three things. The D we can set to be equal to L of 0. Now in Python, array indexing begins at 0. So L0 is the first element in the triple. L1 is the second one, and L2 is the third. MATLAB is slightly unusual amongst programming languages that it begins array indexing at 1. Most computer languages started at 0. So D is the greatest common divisor. Remember, we're not changing the greatest common divisor because the greatest common divisor is the same all the way down. So we're just reporting back D, which is the value we get from calling my GCD. Now this alpha and beta that I've sketched on the board, alpha is equal to L1 and beta is equal to L2, the last element that in the triple that got returned. And so now we just need to define what, we've already defined what D is, now we just need to define M and N. So M is going to be, M, remember, which is the coefficient of A, that's going to be equal to beta. And N, which is the coefficient of B, that's equal to this combination here, alpha minus Q. Now, does it know what Q is yet? Knows what Q is. Knows Q is the floor of A over B. So Q is this quotient here. Floor of A divided by B. He's behind the small remainder. So it knows what Q is, so it's A minus Q times beta. Okay. So with those values put in, with those extra commands put in, this function should now be returning the GCD, as it always did. So it's going to return a triple of elements here. The first entry should be the GCD, and the second and third should be the coefficients for the input A and the input B in that order. That gives you a Bezo's identity. Okay. So we have to execute this function definition. Now, if you're playing with this afterwards, when you're typing stuff and you press return, that just sends you to the next line when you're building up your code. But when you want to actually execute a block of code, you do shift enter. Okay, so shift enter is how you execute the block of code. So that block of code is just defining my GCD. Now we can call it on, so let's call it on 25 and 15. So we get this output. So the 5 is the GCD, -1 is the coefficient of 25, and the 2 is the coefficient of 15. So does that check out? Yeah? 2 times 15 is 13, minus 25 gives you 5. So that, it does look right. And test it again with these two large random numbers. So if I define that equal to L, so the GCD is 21. So if we take L1, so that's the second entry, this entry here, multiply it by A, and take L2, which is the last entry, that should be the coefficient of B, same B here that are stored here. When we evaluate that, it should give us 21. Yeah, it does. Okay. So that confirms that these coefficients that got returned are the correct ones. Okay. So if you've never seen recursion before, did you cover recursion and function definitions in the first year of programming skills? Maybe no. So it's a very interesting thing. It kind of looks wrong when you first see it, because here we're defining the function myGCD, but then we're referring to the function myGCD. Normally, like we would pick that up as an inconsistency. How can you define what something is by referring to the thing itself? But in certain cases, it is fine because it just sends. When you call the function calls itself again, and it repeatedly calls itself. But if you're sure that eventually one of these concrete base cases, these are like the base cases in an induction, if you like. If you're confident that or if you know that eventually, when the function keeps calling itself in different arguments, but if eventually one of these base cases is going to be triggered, and it will actually return some concrete values, then the return statements just unravel all the way up to the very first time that the function called itself. So the values get sent out into L, and then it does the last correction needed to assemble the D, the M, the N, the correct values to return. It does that. Okay. So I'd encourage you to, when you set up the account with SageMath Cloud, when you go in and look at the project that's sitting there, this document will be there for you as well, so you can have a look at that. And I'll also put up on Moodle the equivalent thing programmed in MATLAB as well. Okay. Any questions about it at the moment? Just to any queries? Okay. So it's a very interesting thing. Recursive function definitions. And it does produce code which is deceptively simple. So we were able to define my GCD function with just these few lines, and it almost looks as if we were able to define it without doing any work at all. But that is the nature of this Euclidean algorithm. It just performs these integer divisions, and it keeps putting off the question, what is the GCD? It keeps putting off that question and replacing it with a simpler pair until at the very bottom, one of the pair is 0, and the answer is obvious, and the answers get returned. Okay. Okay. So what we're going to do now is come on to chapter 3, which is where we finally start talking directly about prime numbers. So we've done a lot of work with the concept of divisibility and common divisors, greatest common divisors. And that was laying the ground so that we could talk and make some progress with proving results about prime numbers. Okay. So we've got the definition of a prime number here, but really I'm assuming everybody knows what a prime number is. So a prime number is one which has no factors apart from itself. Okay. And we reserve the word prime for just talking about the positive integers greater than 1. So positive integer greater than 1 is prime if it's no factors other than itself and 1. I mean, you could refer to, like, in a sense, -5 and -7 and -11, they are prime as well, but really they're the same. Really, when you start to examine it in detail, -5, -7, and -11 are really the same primes as these. There is no property that -5 has as a prime number that isn't also, shared and carried by the number 5 as well. Okay? Because we're examining here the operation of multiplication on the integers, positive numbers and negative numbers behave the same under multiplication, really. It's just you have to account for, do you have an odd number of minus signs or an even number of minus signs, and that tells you whether the answer is positive or negative. So you don't lose anything by just studying the multiplicative properties of the positive. And that's what we do. From that definition of a prime number, we straight away get this interesting property, and it's really just a feature of the definition itself. Okay, and that's now that any integer factorizes into prime numbers. Okay? And the way the proof is presented here is as an example of strong induction. So strong induction is where you assume that the result is true for every integer less than some general amount. So we're assuming that every positive integer strictly less than k factorizes into prime numbers. So then we have to prove from this assumption, we have to prove that k itself factorizes as a product of prime numbers. Now k might be a prime number itself, in which case there's nothing to prove, because the number k itself is a prime factorization of length 1. But otherwise, k will not be a prime, and if it's not a prime, by definition it factorizes as a product k1 times k2, as a non-trivial factorization, so neither of these numbers are 1. We're not simply writing k as 1 times k. It's a composite number. It must have a genuine factorization. So here's a genuine factorization. But if neither of the factors are 1, that means they must both be strictly less than k. Okay? Because if they weren't, then the factorization would be bigger than k. So now we've written k as a product of factors which are strictly less than k. But those are covered by the induction hypothesis. By assumption, those numbers factor into products of primes. So you can have the product of primes for k1 times the product of primes for k2, and that gives you k as a product of primes. Okay? So every number factorizes as a product of primes. Just trying to think of a moderately big number that's slightly interesting factorization. 220. 225, I think. So this proof is really just a formal presentation of this intuitive idea that you can start with a large number and start factorizing. Well, we know this has a factor of 5, so you could write this as 5 times, and it would be 45, wouldn't it? 5 times 45. Okay, 5 is a prime number. That can't be factorized non-trivially anymore. 45 is not, though. That has another factor of 5 in it, and times a 9. Again, 5 is a prime number. 9 is not a prime number. That has 2 prime factors of 3. Okay. Now, of course, this process has to come to an end. Okay, if we're starting with a fixed amount, we're factorizing it, we're producing smaller factors. So we're on a downward journey here through smaller factors. Everything will always be positive and bigger than 0. So eventually this is going to finish. So we get this prime factorization here for 225 as 9 times 25, or 3 squared times 25. 3 squared times 5 squared. Now, as I've been saying all of that, I've been very careful to not use the word the prime factorization of these numbers. Okay, so a question that's hanging in the air is this uniqueness. Is 3 squared times 5 squared? Is that the only way to write 225 as a product of prime numbers? The reason why it might not be is that when I did this factorization here, I was making choices about how I branched it at each stage. There was no reason why I had to branch it like that at the beginning. I could have started off 225, and I could have divided it by 45 at the start. And it was, what was it? Sorry, that's what I did do. Sorry. I could have divided it by 9 at the start. So if I divided it by 9 at the start, it would have been by 25. And the 9 goes to 3 by 3. And the 25 goes to 5 by 5. And of course, I've got the same prime factorization again. But why is it that, and if these numbers get very, very large, there could be a very large number of choices for each branching, how you factorize it. How do we know that all those huge number of different possible factorization trees I could draw underneath these numbers, how do I know that they always have the same leaves? This is a tree, well, it's an upside down tree, the roots at the top and the leaves at the bottom. These things are called the leaves. And you end up with prime leaves. If it's not prime, you keep factorizing, so eventually you get prime leaves. How do I know I'll always get the same collection of primes at the end? Okay. Well, we should be cautious about that. We should be slightly skeptical about that until we see a nice, rigorous proof of it. Of course, no matter how many examples you investigate, you will find you do always meet the same collection of primes. So they are unique, but there's a question here of, how do we know that they are unique? How difficult is it to prove that they're unique? Well, it's not too difficult. We'll be proving it in probably not today, but in the next lecture. Is that okay? So we know everything factorizes into primes. This formal proof here, or just thinking about this factor tree process. We've raised this question of what the uniqueness is. And now, I think we'll finish today by just looking at this, this proof here. This is maybe the most famous result in introductory number theory. And this is the proof that there are an infinite number of prime numbers. So although we've only just formally just started, we've only just given the definition of what a prime number is, straight away though, with what we know about divisibility, we're able to prove that there's an infinite number of prime numbers. Okay? So this is quite a powerful, significant result. Okay? Life would be a lot easier if there was only a finite number of prime numbers. Okay? It'd be a lot more boring as well. It wouldn't be a subject of number theory to investigate the structure. The first significant thing about the primes is that there's an infinite number of them. The way I've presented the proof here is as a proof by contradiction. Okay? So remember, in a proof by contradiction, the very first thing you do is you pretend that what you're trying to prove is false. Okay? That's how it operates. So we're trying to prove there's an infinite number of primes. So we pretend there's only a finite number. Why are we doing that? We're pretending there's only a finite number, so we can take that assumption and squeeze it, and eventually squeeze it so that a contradiction pops out. We want to show that a contradiction is inherent in making this assumption. And because we can't have contradictions in the world, true, genuine logical contradictions, because if genuine logical contradictions are around, the whole enterprise falls apart. So we instead conclude that, well, what led to that contradiction itself must be false. Okay? So we're not allowed to pretend there's a finite number, so there must be an infinite. So if there's a finite number, if there is a finite number, you can label them all, and there's a first one and a last one, and you can write them all down in a list. Okay, so we assume that this is the finite list of primes. And then we think about this number capital M, which is gotten by simply multiplying them all together. I'm not writing out a comma-separated list now, but writing out a product of all these numbers and adding 1 to it. Okay? That's this number, capital M. And then we ask ourselves, well, what does divisibility say about this number, capital M? Now, this number, capital M, can't be a prime number. Okay? Because we're pretending that these are all the prime numbers here. Okay? So the first few, like it's 2, 3, 5. By inspection, we know that the beginning of this list. So these numbers are all bigger than 1. So when you multiply them together and add 1, you get a number n that is bigger than all of them. Yeah. This number n is certainly bigger than all of the pi for each i. So m itself cannot be a prime number, because it cannot be one of these numbers here that we've multiplied together and added 1 to. Well, if it's not a prime number, it must factorize. What do I call the factor? Well, yeah. See, we've just proved that every number factorizes into a product of primes. So, let's got a pj. We've just proved that every number factorizes into primes. So n must factorize into primes. But these are all the primes that there are. So we just pick out one of its prime divisors. So we say, therefore, it does have a prime divisor, pj. So pj is one of these numbers along here. So now we know that pj divides m. Okay, because it's a prime factor m. M is not a prime number, so it must factor into primes. So then we know that pj divides m, but also we also know that pj divides this product of P1, P2, all the way up as far as Pn. And the reason it divides that is because it is one of the numbers along the way here. Pj is one of those factors along the way. So clearly Pj divides the product. So we know Pj divides M, Pj divides the product in the bracket, but those two together imply that Pj divides 1. Why? Because 1 can be written as a linear combination of those two. It is simply M minus the bracket. Okay. So it's possible to write 1 as a linear combination of these two numbers. And we know by a property of divisibility, if some number here, Pj, if Pj divides M and Pj divides that bracket, it must divide any linear combination of M and the bracket. So it's a particularly simple one, just M minus the bracket, but that's equal to the quantity 1, so therefore Pj must divide 1. But can a prime number divide 1? Can this prime number Pj divide 1? Well, no, it can't. Because by definition, primes are numbers bigger than 1. That's part of the definition of what prime numbers are. Okay? They are numbers bigger than 1. So this is our contradiction. Okay, yikes. We seem to have concluded that a prime number divides 1. Now, if that happened normally, it's the end of the universe. It's the end of the whole thing. But we made a mistake along the way. And the mistake was at the very start, right? Where we pretended that there was only a finite number of primes. Okay? So this pretense up here is impossible. Okay? So this is a contradiction. So this cannot be said. Okay, so if there are not a finite number of prime numbers, then there must be an infinite number of prime numbers. An infinite number of prime numbers. Now that's presenting the proof as a proof by contradiction. It isn't always presented like that. You can present it. There are many ways of just kind of saying it or presenting it. Sometimes people present it as an algorithm for generating prime numbers. So if you take any collection of distinct prime numbers, so P1 up to Pn, you take any collection of them, multiply them together and add 1, the new number that you produce, it has prime factors, because every integer has prime factors. The prime factors that it has will all be new ones. Okay? So then you can add them to your list. You get a slightly bigger bunch of prime numbers. You do this construction again, you multiply them all together, add 1. This number has prime factors. All of them are new ones, not contained in your list previously. Every time you have a finite set of prime numbers, there's this computation you can do, which will produce a bunch of new ones, the prime factors of capital N. There's nothing stopping you repeating that process without end. Okay? So your collection of prime numbers will always grow. It's not limited by any finite quantity. So therefore, there's an infinite number. Okay. Any questions about that proof? That's all. Okay. So it's the most famous result in beginning number theory. It's definitely something that everybody should know. Everybody should know how to prove. It's like a real classic proof. So next time we'll be moving on and we'll actually be tackling our fundamental theorem of arithmetic and proving it. So that's where we prove the uniqueness of these prime factorizations. Okay, so I'll see you tomorrow afternoon, I believe. Yes. For the next lecture. I'll see you right now as well, but in a different class.